Hello, welcome to the third in the series of lessons on kinetics, and this is dealing with the rate determining step, which has specification reference 3.4.1 as well. So what we want to do in this lesson is to understand that the orders of reactions with respect to reactants can be used to provide information about the rate determining step of a reaction. So first of all, what we need to do is we need to decide or learn what the rate determining step actually is. And so you should consider that a chemical reaction, also known as a reaction mechanism, can have more than one step, even if it doesn't appear so from the balanced equation. And each step does not have to have the same rate. In fact, the steps pretty much always have different rates. And the step with the slowest rate is what is known as the rate determining step, or the rate limiting step. Now, all the species, actually including catalysts and any intermediaries that might be in the reaction steps but not appear in the equation, all the species that are in the rate equation are in the rate determining step. All right, so if they are in the rate determining step, that means by definition that they're in the rate equation. However, not all the species in the chemical equation need to be in the rate equation, i.e. if there's something in the chemical equation that's not in the rate limiting step, then it's not in the rate equation. And lastly, the order of a reaction with respect to a reactant shows the number of molecules of that reactant involved in the rate determining step. So if the order of the reaction with respect to reactant A is 1, then there is one molecule, one particle of A in that rate determining step. Likewise, if the order with respect to B was 2, then there are 2 B particles in the rate determining step. So let's now have a look at an example. The example we're going to use is ozone decomposing into oxygen, which is a reaction that's catalyzed by chlorine free radicals in the atmosphere. And so that reaction has 2 steps to it, and the first step would be written as this. So we've got a chlorine free radical, which we'll write like so. And we have ozone in the atmosphere that forms an intermediary free radical, written as such, and oxygen gas. So that's step 1. Let's put a 1 here. And step 2 to this reaction is this intermediary free radical reacts further with another molecule of ozone to reform the catalyst chloride free radical and produce more oxygen, like this. So they're the 2 steps to the reaction. And what we should consider now is the speed of each individual step. And as it happens, this step here is the slow step, and this reaction here happens very fast. So if you remember what we said about the rate determining step, it is the slower of the steps. So this step here is the rate determining, or the rate limiting. So that's the rate determining step. So the next thing we can do is we can use this information in order to generate a rate equation. So let's start off with a fairly generic form of the rate equation. So we know that the rate is going to be equal to the rate constant times the reactance. Now, we only include the slow or rate determining step. So the reactants in that step are the chlorine free radical. So we need the concentration of the chlorine free radicals and the concentration of ozone. So, but we don't know what orders they are yet, so let's just list them as M and N. And in order to work out the orders of this rate equation, we need to remember the previous slide, which said that the orders correspond to the number of particles, let's say, of the reactants in the slow rate determining step. So you can see from step 1 that there are both one particle of chlorine free radical and one particle of ozone in the rate determining step. So both M and N are 1, so we can write the rate equation simply as K times the chlorine free radical times the concentration of ozone. So now what we'll do is we will have a look at reaction mechanisms, and what we will do is we can work out the reaction mechanism if we know the reactants that are in the rate determining step. So here, let's take this reaction here where we've got 2-bromo 2-methyl propane, and we react that with the nucleophile hydroxide ion to give 2-methyl propan-2-ol and bromide ions, right? And the question wants us to work out what the reaction mechanism is. So we can consider two possibilities. Let's look at the first possibility. So first of all, let's write down 2-bromo 2-methyl propane. So you can see that that's going to be a CH3 group, methyl group connected to a central carbon, another methyl group, another methyl group with bromine. So there we have 2-bromo 2-methyl propane, and we're going to react that with hydroxide ions, and that might give us 2-methyl propan-2-ol, which is written with the methyl group attached to the carbon and the other methyl groups as before, but instead of the bromide we have the hydroxide ion in the molecule, and floating around instead is the bromide ion. So that is one mechanism where simply the hydroxide ion replaces the bromide ion as so. Now, if that was the reaction mechanism, then clearly we have two reactants, hydroxide and 2-bromo 2-methyl propane, and so they would necessarily, by definition, appear in the rate equation. So let's hang off looking at the rate equation for now and consider the other alternative reaction mechanism. So again, we're going to start with 2-bromo 2-methyl propane. Right, but instead of the hydroxide ion directly replacing the bromine atom in the molecule, what we could possibly have is the bromide ion breaking off. So this bond here breaking, bromide taking the electron with it to leave two intermediary species that look like this. So you've got the central carbon, and it's lost the electron because the bromide has gone off with it. Right, and the methyl groups are unaffected relatively. So you have this molecule, this, let's call it an ion, and a bromide ion gone off as well. And that could happen as the first step of a reaction, but these ions are relatively unstable, they're quite reactive, and this ion with the positive charge on it is going to be quite attractive to the hydroxide ions that have the negative charge floating around in the vicinity. Alright, so you would have another step of the reaction which would be given as such. That's the plus charge, right? And then you would have the hydroxide ion floating around nearby, and that would give you the final product, 2-methyl propantool, as before. In step 2. So let's call that step 1 and step 2. And when you look at these two steps in the reaction mechanism, you can see that the second step is going to be first, isn't it? You've got a positively charged ion and a negatively charged ion in close proximity to each other, and they're going to react quickly. So that's going to be the first step. Alright, and this breaking of the bond in the 2-bromo-2-methyl propane is clearly going to be the slow step. So that is the slow and therefore the rate determining step. So the question remains, which of these two reaction mechanisms is correct? And in order to decide, as if to adjudicate, we're going to have a look at the rate equation. And the actual rate equation was worked out using experiments, right? And it is rate equals the rate constant times the concentration of two-bromo-2-methyl propane so there's the rate equation, and as you can see, the only reactant that is in the rate equation is 2-bromo-2-methyl propane, which gives you, which of course comes from the slow step, and therefore you can see that the mechanism 2 is the mechanism that actually happens in practice. So here's another example, and this is an interesting one, slightly more difficult. So when nitrogen monoxide can, when it reacts with oxygen to produce nitrogen dioxide, the chemical equation is something simple like this. 2 nitrogen monoxide molecules plus 1 oxygen molecule react to make 2 nitrogen dioxide molecules. Simple as that. However, the reaction actually goes forward in 2 steps. The first step being this one, nitrogen monoxide molecule reacts with another nitrogen monoxide molecule to make this compound N2O2, and the molecule called dinitrogen dioxide. And then what happens in step 2 is that the dinitrogen dioxide reacts with an oxygen molecule and makes 2 molecules of nitrogen dioxide. And what we have to do is we have to figure out the rate determining step. So we can use the rate equation, and we're given the rate equation, usually calculated by experiment. So the rate equation here is rate equals the rate constant times the nitrogen monoxide concentration to the power of 2 times the oxygen concentration to the power of 1. Okay, so what we can see from this is that there are 2 molecules of nitrogen monoxide in the rate determining step and 1 molecule of oxygen in the rate determining step. But that's not consistent with either of the 2 steps. However, in step 1, you can see that 2 nitrogen molecules, 2 nitrogen monoxide molecules are involved to make the dinitrogen dioxide. So what that means is that step 2 is the rate determining step, because in step 2 there's an intermediate molecule, the dinitrogen dioxide, that's derived from the 2 molecules of nitrogen monoxide in the rate equation. So step 2 is the rate determining step. So just to recap, our learning objective was that we understand that the orders of reactions with respect to reactants can be used to provide information about the rate determining step of a reaction.